Welcome to today's webinar presented by Delubal Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's webinar is the NBC 2015 Modal Response Spectrum Analysis in RFEM. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and also a technical support and sales engineer, and we are located in Philadelphia, Pennsylvania. My colleague Alex Bacon will be your moderator, answering any questions you may have. He's a technical support engineer, also located in our Philadelphia office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within the same dialog box. If by chance we don't get to all your questions, I will certainly send you a follow-up email afterwards. So as far as the content over the next hour today, I want to give a brief introduction to the RF-DYNAM Pro add-on module. So these are these add-on modules for dynamic analysis embedded within our main program, RFEM. And then we'll move on to our example for today by running first a natural frequency analysis. Now, in order to do this, we must set up our mass cases and mass combinations. We'll run that natural vibration calculation, and from here, we'll determine the frequencies, mode shapes, and mass participation factors. Then we'll move on to a modal response spectrum analysis. So for this, we'll set up our calculation options specifically according to the NBC 2015. We'll generate these equivalent loads and we export them back out to that main program, RFEM. And finally, towards the end, we'll take a look at story shear and story drift considerations, again, specific to the NBC standard. So RFEM is the main finite element analysis program, and this is where we can fully model our structure, and we can load it, and we can run an analysis for these basic static loads. But when we're wanting to take into consideration a dynamic analysis, we need to utilize our RF-DYNAM Pro add-on modules, and there's actually 4 separate add-on modules within this category. The first is RF-DYNAM Pro Natural Vibrations. So this is a prerequisite module for the other 3. You must at first run this natural vibration analysis to determine the mode shapes of our structure. It'll give us other information such as natural frequencies, time periods, and accelerations. Now, the other add-on module is RF-DYNAM Pro Force Vibrations, and this will allow us to do a linear time history analysis. It's also possible to do a multimodal and multi-point response spectrum analysis, and this does include the various standards like the NBC, the ASCE 7. But there's a couple pros and cons. The first is a pro multi-point response spectrum analysis will allow us to assign different response spectra to different supports in our structure. Now, the downside is that utilizing this add-on module for response spectra, we're not going to be able to export out the equivalent loads back out to RFEM. We're also not going to see options such as accidental torsion to include, which is required by most of the standards. The third add-on module is actually a module extension of force vibration. So this is nonlinear time history. And so you must have force vibrations in order to activate this module extension. And this will simply release 2 nonlinear solvers into this force vibrations add-on module. And that includes the implicit numeric solver and the explicit solver. So I've done a couple of previous webinars on both a linear and nonlinear time history analysis. You can find recordings of those on our YouTube channel and our website if you're interested, because we won't be getting into these add-on modules today. But rather we'll be focusing on RF-DYNAM Pro equivalent loads. And this allows us to run a multimodal response spectrum analysis, again, according to the NBC, the ASCE 7, Eurocode, and many other standards. And for this, we can generate those equivalent static forces and export them back out to RFEM. Okay, so one final thing to discuss here is the method of analysis according to the NBC standard. And we can find this discussion in 4187 of the code. And there's some certain stipulations on which method we can apply to our structure depending on which categories we fall in. So the equivalent static force procedure is a more simplified method, and we can find this in Article 41811 of the standard. And this tells us that when the importance factor times the site coefficient times the spectral response acceleration at 0.2 seconds is less than 0.35. Also, when we have a regular structure that's less than 60 meters in height and our lateral period is less than 2 seconds, or even for irregular structures, and we refer to table 4186 for irregularities with a height less than 20 meters and a lateral period less than 0.5 seconds. Well, then this equivalent static force procedure can be applied. So in summary, we can somewhat assume that this simplified method can be used for shorter, symmetric, more straightforward structures. Now, for anything else, then we would refer to the dynamic analysis procedure given in 41812. And within this section, we are given two different methods, the response spectrum method or the time history method. So we'll be focusing, of course, on the first method for today's presentation. Now, this should be applied to irregular structures. And again, we refer to this table 4186 that gives us some guidelines on what exactly is an irregularity, and this might include stiffness, weight, or geometric irregularities. Okay, so we will begin with our example today. So you can see for the sake of time, I have already modeled this multi-level story structure, and we're in our main program RFEM, General Finite Element Analysis. So looking at this structure, we can view the materials here, concrete 30 MPa. If we're interested in the height of the structure, we can use our measure tool to see from the top to the bottom. We have a height of 35 meters. So looking at some of the elements here consisting of surfaces and members, we have our columns. And when I double click just to take a look at these, the member type is a beam. And if we're interested in the diameter here, it's 508 millimeters. As far as the slab elements, these are just standard surfaces within the program. Again, same material. The thickness is set to 350 millimeters. And looking at our wall elements, we can just select one of these. Same concept, except for the thickness has been modified to 300 millimeters. So we have also taken the liberty here to apply some loads to this structure. And you can see within my drop-down box just three simple load cases: dead load, live load, snow load. So when I display the dead load, you can see that these are just general surface loads applied at each level, 5 kilonewtons per meter squared. When I look at my live load, it looks identical, same surface loads. I've just increased my magnitude here to 28 kilonewtons per meter squared. And finally, we have a snow load case at 2 kilonewtons per meter squared. Now, if we wanted just to run the general static analysis with any one of these load cases, we could, of course, do so within the main program. But to not spend too much time here, we're really interested in that dynamic analysis. So what we need to do is to open up our RF-DYNAM Pro add-on modules. Now, the add-on modules can be found here within our project navigator. So you can see our long list available over on the left. Now, add-on modules are also available within our drop-down box here, and they're categorized a little bit nicer. So maybe we pull open the dynamic options and we launch RF-DYNAM Pro. Now, this is just a simple dialog box that will open up within the main program RFEM. And what you'll see here are the 4 different dynamic modules that are available to us that we just discussed within the PowerPoint. So you'll notice RF-DYNAM Pro natural vibrations being the prerequisite is automatically selected here. So we begin with that natural vibration analysis. I'm also going to activate the mass combinations tab. So notice that I now have an additional tab here called mass combinations. Then I'm really just going to move from left to right within these tabs. So moving on to mass cases, my first mass case description is going to be dead. Now I'm going to uncheck here from self-weight of structure. If I leave this checked, and I'm going to import in here, remember my load case, my dead load case back in RFEM, I'm importing in that dead load case. Well, that load case already considers self-weight. So if I were to have this checked, then we're accounting for it twice, which would be incorrect. So creating a second mass case, what I can do here is just to make a copy of my existing dead mass case, and we'll call this one live. So of course we want to import in here from our load cases our live load. And remember, this comes back from RFEM. And then we have our third and final mass case, and we'll call this one snow. And we're going to import in our snow load case from RFEM. So pretty simple. Now, you do have the ability here to manually define additional masses. So let's say that we did not fully define all the masses within these load cases back in RFEM. Well, you can highlight and select any one of these options here, and notice now we have additional tabs up at the top. So for example, nodal masses. Well, this gives me the ability here just to select any nodes graphically, and then I can input in a mass as well as a mass moment of inertia if I'd like to. So we won't be doing that for today. We'll assume all of our mass is considered within these load cases that we have imported in. So moving on to the mass combinations. Well, when we refer to the NBC standard and Article 4182, this tells us how we can combine all of these different weights. And for today, we're going to apply all three of these mass cases into my first mass combination, and we can even give it a mass combination description 1. But the thing that I want to do, referring to the standard, is to modify this to include, let's say, 60% of my live load. So I put in a factor of 0.6 in front of my live load, and then my snow load, I'll set a factor of 0.25. But I still want to consider 100% of my dead load for these mass cases. So we'll just go ahead and leave that factor at 1.0. So you have the ability to create multiple mass combinations here. So we can do so in the lower left-hand corner. You can make copies, you can create new mass combinations, because maybe we want to consider some different combination types where we don't include live load, or maybe we don't include snow load, just to see how our natural vibration analysis changes with those different considerations. And finally, we have our natural vibration cases tab. So the first thing to do here is to give it a description. So we'll give it a natural vibration case 1 as a description. The number of lowest eigenvalues to calculate. You can see the default here is set to 4. Well, this really depends on your structure, and I'll actually get into a discussion about maybe what is the right number of eigenvalues to solve for in just a minute. But we'll set this to 10 for our example today. The scaling of the mode shapes. So this just will scale the magnitude of our mode shapes. And you can see this first option here only considers the translational part. So we'll square them, we'll add them together and take the square root, and then we will just simply scale that to 1.0. The second option will choose the max translational part and set that equal to 1.0. The third option here is the exact same concept as what we see above, but it also considers the rotational parts. And finally, the fourth option, well, this will be used internally, where the modal masses are set to 1 kilogram. So sticking with the first option today, we'll just move forward with the square root sum of the squares. Under the calculation parameters, we need to define our acting masses. So we can choose a mass case here from our dropdown, but we just created that mass combination on our previous tab. So we'll go ahead and utilize that for today. We also need to define in which directions or about which axes our mass is acting. And this is actually influenced by this type of mass matrix. And as far as the mass matrix, you'll notice the first 3 options are all diagonal matrices. And this is where the masses are lumped at FE nodes. So this first option is where masses will be acting in the translational X, Y, and Z directions only. And this is relative to our global axes in the background here in RFEM. The second option is translational and torsional degrees of freedom. So you'll notice that we now have the ability to activate about the X, Y, and Z axes. Well, the difference here is that both the translational and the masses acting about the longitudinal axis of either a member or a surface are now considered. And we then have our third option here where translational and rotational degrees of freedom are considered. Well, this just will activate all 6 degrees of freedom. We also have the consistent matrix, and the consistent just means that the masses are not lumped at FE nodes, but rather shape functions are going to be used with this option. And finally, the unit matrix, and this is just going to apply a 1 kilogram mass at each FE point, and translation and rotation are considered, and this is used more for a numerical analysis. So for today, I only want to consider the translational degrees of freedom, but I am going to uncheck here in the direction Z. And the reason why is because my seismic analysis for my example today, I'm really only concerned with the lateral direction. So in the global X and Y directions. In the Z, I don't really have any excitation I want to calculate for the example. So therefore, there's no reason to solve for the natural vibration analysis in the Z direction either. The method for solving the eigenvalue problem, well, this is just our solver, and this is really more of a performance setting rather than accuracy. And you can read more about the various solvers within the manual, which you can access here with this little question mark at the lower left-hand corner. The stiffness modification, so we won't be doing anything with this today. Maybe just an example where you'd want to use these options for response spectra analysis relates to accounting for P delta. This is a linear analysis, so P delta is not automatically considered, but there are ways to do it. And in my previous webinar, according to the ASCE 7 for a response spectra method, I did show how to consider a P delta analysis. So again, you can refer to that recorded webinar on our YouTube channel or website. But for today, we won't be applying any of these settings. We'll just leave this as no stiffness modifications. So when we have entered in all of this information, we want to begin by clicking OK and calculate. So right now the program's just running through that natural vibration analysis. Now keep in mind the number of eigenvalues that we set the program to solve for is going to definitely influence how long this calculation time takes. So for 10 modes, it really doesn't take too long. You can see that our results are available to us now fairly quickly. And the program will bring us back into RFEM. So we're technically still within this RF-DYNAM Pro add-on module, which we can see here from our drop-down box, but I'm now viewing my various mode shapes graphically. So what I can do is to access my table down at the bottom. And when I take a look at table 5 dynamic analysis, within my drop-down box here, I've only solved for that first natural vibration case, so it's available to me here. Well, I can go ahead and take a look at this first tab for my 10 different modes, and I'm viewing the accelerations, angular frequencies, natural periods. Then I have my drop-down box here that shows me my 10 different mode shapes. So if I want to kind of see graphically how the structure is responding for the different mode shapes, we can view those here. Now, probably the most important tab is going to be this last one, the effective modal mass factors. And again, we see our 10 different modes given to us here. And most importantly, we have this summation row at the bottom, and I'm viewing my effective modal mass factors for each of the modes. And my summation at the bottom is giving me 95% for both the X and the Y direction. Well, when we refer to the NBC 2015 commentary, we have this requirement that we must meet a minimum of a 90% mass participation in the directions that we're considering, which in our case is in the X and Y. Notice Z, everything is set to 0 because we did uncheck that option. So we're certainly meeting that 90% minimum here with our 10 modes, so we can probably continue to move forward. But there might be the question, well, you know, for my structure, I tried this, I'm not meeting the 90% mass participation, what can I do? Well, the easiest answer for that is just to solve for more eigenvalues. So remember, we set this equal to 10 when we ran, or when we were inputting in all of this input information within the add-on module. Maybe you increase this to 20, to 30, to 40 even. There is a scenario though where you're really taking into consideration a high number of eigenvalues and still not getting great mass participation. And you might want to begin to look at your various mode shapes. And for example, we can take a look at mode shape number 7 here with 0.1% mass participation in the X and Y. Well, some of these might be considered more local modes where we have just a single member kind of responding or single surfaces. And in that scenario, maybe we need to consider how our mass is distributed, and maybe we use some of those options I showed you before where we manually define some masses at nodes and at lines and so on. So definitely don't want to have a whole lot of local modes. Instead, we like to see some, at least one dominant mode, of course, in each direction as well. And in our case, our dominant mode in the X direction is mode number 1, and then mode number 3 would be our dominant mode in the Y direction. So again, very important to make sure that we're meeting those minimum mass participation requirements. So now that we have completed the natural vibration analysis, we can move on to a response spectra analysis. So I will launch the add-on module again, and I can just click that open here within my panel, RF-DYNAM Pro. Now, back on this first tab here, this is where we want to activate this fourth option, RF-DYNAM Pro equivalent loads. So my natural vibration analysis is still active. Nothing's been cleared here with all of these tabs. It still exists. But what I have added is a couple additional tabs over here on the right-hand side. And you'll notice that with the response spectra, I have the ability here to select a standard from my dropdown. And you'll see here the IBC and the ASCE7. We have the Eurocode, many other international standards as well. But today we'll be focusing on the NBC 2015. Now this table over on the right will be automatically updated according to which standard you're choosing. Now notice you can also choose a user-defined option here where you can just input the accelerations as a function of time period manually. So moving forward with the NBC 2015, we want to give this response spectrum a description, so we'll call this one the design. Now, this is an important topic, and with the type of spectrum here, we have a drop-down box, and we have either the design spectrum for linear calculation or an elastic response spectrum. And at the end of the webinar, I'm actually going to get back into the difference between these two. But to begin with, I'm going to select the design spectrum. And then you'll see here that I have my input data where I need to, as a user, put in the spectral acceleration for a period of 0.2 seconds, 0.5 seconds, 1 second, and so on, clear up to the peak ground acceleration. And this is all specific to the standard or where your project is located, and maybe referring to the NBC standard for these values. Well, I want to take advantage here of a helpful tool that we have on our website. So if you go to delubal.com, under the Solutions tab up at the top, you'll find the GeoZone tool. And what we have done here is you'll notice that we have integrated Google Maps technology along with these various standards to give us information about snow, wind, and seismic data. So within our standards dropdown, you can see we have quite a few number of standards. The ASCE7 is shown here, many European standards all over the world, and of course the NBC 2015. So I click on my seismic option here, and then I need to define, maybe with the city, the address, whatever it may be, the location of my project. So we'll assume for today that our project is in Calgary. Well, when we choose this option Calgary, we select from the drop-down box here. Here is my acceleration at 0.2 seconds, and the value is given at 0.19 G. Well, I continue to do so here for my acceleration at 0.5 seconds, and my map will automatically update, and my value over on the left here is now 0.132. So I want to take note of all of these values, again, including the peak ground acceleration, and to record those down, because this is the information that we're going to need to put into the DYNAM Pro add-on module. So again, just a very user-friendly way rather than having to kind of filter through those maps manually within the NBC standard, again integrated with Google Maps technology. Now, the first few requests are on us. Those are free, but if you plan on utilizing this map quite heavily, then you might want to consider purchasing a GeoZone tool package up here in our web shop, which you can find up at the top of the page. Okay, so now that we have determined what all of these values are, like I said, we need to input this into this table. So we'll begin at 0.2 seconds, and the value here is going to be 0.19. The next value is 0.132, and 0.1, 0.043, 0.01, 0.006, and finally the peak ground acceleration will be 0.12. We do need to choose our site class, and from this drop-down box, we can choose site class C. We continue scrolling down further, and we're going to get a few other coefficients here. And the first is to set the importance category. So we'll set this to normal. And notice my importance factor here is set at 1.0. We also have our RD and RO variables, and these come from table 4189 within the NBC. And for today, we have a concrete structure. We're assuming conventional construction, and the seismic force resisting system will be set to shear wall. So for example, today, our RD value will be 1.5 and our RO will be 1.3, which is actually the default settings here. Now, these factors are considered for the response spectrum when we have the type of spectrum set here to design. So again, I'll get into this later, but you will want to input in this information, which is considered here. So now that we are done inputting in all of this information, we can move to our next tab here, the dynamic load cases. And the first thing to do is to give it a description. So we'll call this one design once again. Now notice everything's grayed out here, and that's because these are referring to those additional DYNAM Pro add-on modules that we didn't activate under that first tab. So the only thing that is activated is this response spectra for the equivalent loads. We do want to assign a natural vibration case to it. So we only have one natural vibration case, so of course we'll use this as our option. The equivalent force analysis. So this is where we're going to assign the response spectrum in the X, Y, and Z directions. Now, as I mentioned today, we're just going to consider the X and Y directions. We're not accounting for excitation in the Z direction. But we need to assign the response spectrum from the previous tab to these directions as well. Well, we only have one response spectrum that we just defined, so of course that's the only option available here. Now, the factor, I'll get into this later, but this does allow us to take into consideration some additional factors or to scale up this response spectrum if we need to. We can consider accidental torsion. And we want to refer to sentence 418.12.4 within the standard, where the code tells us that we need to look at the plan dimensions of the building perpendicular to seismic loading. And we would take 10% of this and consider it for this accidental torsion. Now, of course, there's a few more criteria points within the standard of when we should and shouldn't apply this accidental torsion. So it's all relative to your project. But for today, we will take this into consideration. Now, looking at the plan view in the X and Y directions of my structure today, this is 20 meters. So to take 10% of that will result in 2,000 millimeters of accidental torsion for that eccentricity, so to speak. The combination of the modal responses. So you can see here we have either the SRSS or the CQC rule. And for this, I'll go back to the PowerPoint to explain this in a little bit further detail. So you'll notice that we have a series of equations here, and this is for the equivalent load generation. And each one of these sets represents an excitation in the X, Y, and Z directions. So the first set here would be excitation in the X, the second set is excitation in the Y, and the third is excitation in the Z. Now for today, we don't have this third component down here, but just for explanation purposes, let's continue on with assuming that we have excitation in the X, Y, and Z. Well, over on the left-hand side, this is our unknown. These are the equivalent loads that we're trying to calculate here in the X, Y, and Z directions that will eventually be applied to every single FE mesh point within our structure. Now, over on the right-hand side, these are known. So, for example, we have the participation factor given to us first. The second term is going to be the mode shapes, and you'll see those are in the X, Y, and Z directions. We also have the spectral acceleration according to the NBC 2015 as a function of our building period. And finally, our last term here will be our mass. So these loads are generated for each mode shape, and the question is, well, how do we combine these modal responses? And it's with one of two methods. The first is the square root sum of the squares. So it's exactly as it sounds. We're going to take the square of each modal response, add them together, take the square root. So fairly straightforward there. The other option is going to be the complete quadratic combination, the CQC rule. And for this option, you'll notice that, again, we're going to sum up and take the square root, but we've introduced now an additional variable epsilon. And this is the correlation coefficient given by this equation shown here. Now, there's something unique about this, and you'll notice that there's an additional variable D, and this is the viscous damping value. So damping can actually be considered when we are utilizing the CQC rule, and that is a huge difference between utilizing the SRSS rule where damping cannot be considered. Okay, so going back to our example then today, we'd like to utilize the CQC rule. Notice when I click on it, I get an additional damping tab up at the top. With the SRSS, the damping tab will disappear. I also have the ability to apply the signed results using the dominant mode. So in either scenario, we're taking the square root of these results. So we're inevitably going to lose that signage. Well, the program has the ability to determine from these mode shapes, which I'll get into in just a minute. There are my 10 different mode shapes here. Under this option in this dropdown, I have the 10 mode shapes again available to me, or I can just have the program automatically assign the dominant mode. So either you can manually choose how to apply your signage, or maybe you choose this automatic option. The program will determine in both directions what the dominant mode is. Over on the right-hand side, the options to generate load cases. So what we want to do is to export all of these modes, and we'll see 10 of them in our scenario currently. Export them as load cases where we can view the loads in the X and Y direction, also considering accidental torsion. And so we're going to leave this checked, and this will make a little bit more sense when we are actually running our analysis and can take a look at those individually. The second option here is to create those result combinations, and these are the modal combinations that we're going to combine according to the CQC rule over on the left. The third option is the combination of directional components. So referring to the standard again, sentence 41881C, well, this gives us the 130% rule. So essentially there are some scenarios where, maybe we consider each orthogonal direction separately, but there's other cases where we need to consider 100% of the X plus 30% in the Y and possibly 30% in the Z if we had that activated as well. Now, the same goes for 100% in the Y, 30% in the X, and 30% in the Z, and so on. So we can leave this activated, and we'll see this as a result combination as well. The third tab is the damping tab. So if we want to consider damping within the structure, which remember again is only available because we chose the CQC modal response combination, we can choose either Rayleigh damping with an alpha and beta coefficient, or Leer's damping. And Leer's damping is probably what we're all a little bit more familiar with. And for a concrete structure, we might see something like damping set at 5%. So we can input in that 5% here. Now, Leer's damping can also be set separately for each mode shape. So if you don't want to use that 5% for every single mode, you have the ability here to set that individually. For today, we'll just move forward with the 5%. And finally, this mode shapes tab, which I briefly touched on. So this is showing me my 10 different mode shapes. This information is absolutely nothing different than what we viewed with our natural vibration analysis back in RFEM. It's just given me a summary again here. Now, if I hadn't run that calculation yet, this table would be empty and I'd have the ability here to calculate the mode shapes. But we ran that calculation, so that table is given to me. Now, again, we're seeing the mass participation factors, so that 95% in both the X and the Y direction. And there's something important that I'd like to point out here, that we have the ability to deselect modes based on a certain mass participation factor input that I put here. So for example, anything less than 5%, I want to deactivate. And you'll notice that when I choose this option, I actually have 4 modes here that are completely deactivated, and I only have 6 that remain active. And that's just because these particular mode shapes really are not contributing to the overall mass participation much at all. And the important thing to note here is that this is a great tool, but we still have to make sure that we meet that 90% minimum here for our summation. And without those 4 modes considered, I look at my X direction, I have 93%, and I look at my Y direction, I have 90.7%. So this is important because if you have many different eigenmodes, a lot of local mode shapes, you can deactivate them. It's going to increase your solution time. You're going to see your results back in RFEM in just a minute. We're not being bothered with all of these load cases that really don't contribute much to the mass participation. Okay, so now that we have input in all of this information for our response spectra analysis, we are ready to run the calculation. And for the sake of time, I have already done so. It does take just a minute, but let's assume that we ran that calculation, just like what we saw with the natural vibration analysis, will immediately be thrown into RFEM here. And within the table 5, we see our dynamic analysis. We see the natural vibration case still available to us, so we can switch back and look at those different mode shapes. We now have our dynamic load case here, and we gave that description design. So probably the easiest way to kind of understand what's going on here is to take a look at our load cases and combinations. So activating this dialog box, you'll now see here that instead of just seeing my dead, live, and snow load, I have many more load cases here. Well, these are the equivalent loads that were exported from RF-DYNAM Pro into RFEM as general static loads, really, to represent our seismic analysis. And you'll notice that each of those now 6 mode shapes, because we deactivated 4 of them, are all given here in the X and Y direction, considering both positive and negative torsion. So what might be interesting to us is taking a look graphically at what these loads look like. And I can tell you that if I were to activate the loads right now, they will be displayed at every single FE mesh point within this model, which is quite a few loads. So rather than kind of showing you something that really looks too overwhelming, let's just take a look at a single surface. And even with a single surface selected here, I'm only viewing my applied loads at my visible node shown here. But just know that underneath the hood, these loads are being applied to every FE mesh element on this surface. So you can imagine the finer the FE mesh, well, the more loads we're going to generate. But scrolling in here, what we're going to see at each FE mesh point is a load in the X, a load in the Y, and of course our accidental torsion here for our moment. So that's what's being exported out to the program for all of these different load cases. So going back to our load cases and combinations, let's jump to our result combinations tab. And you'll see here our first result combination is in the global X direction. And when I take a look at which load cases are considered, these are all of my load cases that were exported out only in the X direction, considering our accidental torsion as well. Under the calculation parameters, we're seeing here the CQC rule, because this is what we told the program within the add-on module, how we want to combine those modal responses. And furthermore, the program has automatically assigned the signage according to the dominant mode shape 1 here. Well, looking at the result envelope in the y direction, exact same concept, but these are going to be all of my mode shapes in the y direction. My calculation parameters, again, according to the CQC, but my signage is according to the dominant mode in the y direction, which is mode shape 3. And finally, we have our result envelope for the 130% rule. So all that we're going to do here is take result combination 1, we're going to add it to result combination 2, and you can see these over on the right-hand side, but we adjust our factors. Our factor is 1.0, and I can expand this out so you can see this in the x direction and 0.3 in the y direction. Taking a look at result combination 4, same concept, we just reverse those factors of 30% in the x and 100% in the y. Now keep in mind, we can create new result combinations here down at the lower left-hand corner, and maybe we move our 100% rule over to the right-hand side. We also can combine these additional load cases here, dead, live, and snow load. So if we're wanting to create a combination according to the NBC standard that includes dead, live, snow, and earthquake, this is where we do so within this result combination tab. So going back to RFEM then, we now have all of these load cases and result combinations exported, but we haven't actually run our calculation yet to see how our structure is responding under these equivalent loads. So before I run a calculation, I want to discuss story shear and base shear before I continue. So RFEM is a general FEA program, meaning that we don't just do building design, but really you can do domes, you can do finite element of connections, fabric tensile structures. So we don't really have the concept in the program of stories or floors. So when it comes to determining story shear or the base shear, we need to utilize a helpful tool here to help us determine what that information is. And what that will be is with the use of a result beam. So what I'm going to do is to create my result beam before I run my calculation. And what I'll start with is to turn this into a wireframe view, and I'm going to view a plan view of this structure. So I'm technically looking down at the top of the structure. I'm going to highlight all of these nodes right here at the center. So when I turn this back into isometric, you can kind of see that we have these nodes highlighted in red at every single story. So those were just something that I added in manually. I'm going to hold down my control key, and I'm going to just copy, move and make a copy here of these nodes. And it really doesn't matter in where you're placing these. What does matter is that they're at the same elevation here as our structure. So we created each one of these nodes to represent each one of the stories here. Well, I'm going to take this a step further by drawing a new beam member. And the member type here is actually not a beam, but it's going to be a result beam. So result beams are very special because what we can do here, if I go under my detail settings, is I actually can sum up the results within a certain area, or in our case today, from listed objects. So what we're going to do here is to sum up the internal forces, the stresses of our entire structure, and we're going to represent them in a beam type format. And this will make sense as we continue on, but the included objects here will be all surfaces, all members. I don't have any solids for this example, but it doesn't matter. We can just leave this as all as well. I do need to assign some type of cross-section for this result beam. It doesn't matter. We're not assigning additional stiffness to the structure, so the cross-section can be arbitrary, so we choose what we already have defined for our columns. So when I click OK, I'm going to select the bottom node, and then I'll click up to the top node. I'm going to use this additional tool here to connect my lines or members to highlight over this entire result beam, and that's just to break it apart at each one of these nodes. So when we look at a rendered view here, we can see that this really just looks like one really tall column. And we want to run the calculation now with this result beam considered. And I don't need to worry about adding a support to the result beam. I'm not going to apply any additional loads. It's really just a tool to help us interpret our results. So what I'd like to do now is to run a calculation. Now you'll notice within RF-DYNAM Pro, all of those load cases were cleared out when I made changes to the model. So no worries, we would just run that calculation again by going to calculate, calculate all. So again, for the sake of time, I will jump to an already saved model here. And let us jump down to one of these result combinations that we were previously viewing in the X direction. Well, once we run this analysis within RFEM, we can turn on our results. And what will be presented here is our global deformations of the entire structure, so 31.4 millimeters. But more importantly, what I want to activate here are my member internal forces. And I'm going to highlight here only this result beam, and I'll create a visibility by the selected objects. So what the program is doing, and I can kind of change this orientation here just so that it's a little bit easier for you guys to see. This result beam, I have activated for the member internal forces of shear in the local Z direction. So you can see that the local Z corresponds with my global X direction. Well, this is summing up the shear forces for my entire model and representing it to me here as a single beam member. So my story shear up at the top is going to be 1,003 kilonewtons. When I look at my story shear from my second level to the top, it's going to be 1729 minus the 1,003. For my third level, it's going to be the 2218 minus the 1729 and so on. And we continue to do that for each one of these stories clear down to the bottom because I'm very interested in the base shear, of course. Now the base shear in our instance today would be this 3679 minus the 4255. We might be wondering, well, why is our shear bigger at our first story? Well, remember, we have much more mass at this location than what we see at our base level. So story shear is something that is, I'd say, a little bit more complex when we're trying to relate this to the code and what values are given to us within RFEM. So I'd like to take just a minute here to jump back to this PowerPoint to explain base shear considerations according to the NBC standard. So we know from sentence 418.12.5, the code tells us that the elastic base shear from the dynamic analysis is represented by V sub E. So this base shear has no factors included whatsoever. It's just the pure and simple dynamic analysis base shear. Well, from here, we take a look at 418.12.6 to determine the design elastic base shear V sub ED. In order to get V sub ED, we're going to take VE from this previous step here and multiply it by this factor. Now, this factor is going to be the max of either the set of equations on the left or the right. It must be less than 1.0. We don't necessarily always apply this factor, so you do need to refer to the code to see if this is applicable for V sub ED. Then from here, we refer to 418.12.7 to calculate the design base shear, V sub D. Well, V sub D will just simply take V sub ED that we calculated in the previous step, and we multiply it by IE and divide by RD and RO. So then we refer to section 418.11, and this goes way back to the equivalent static force procedure for the lateral earthquake analysis, and this is represented by the variable V. And the code tells us that if VD, which is our design base shear, divided by V, which comes from the equivalent static force procedure, which can, by the way, probably be determined with hand calculations, if this ratio is less than 0.8, or depending on where your structure falls into which category, it could be less than 1.0, then we need to scale VD to this minimum 80% of V or 100% of V. So if we're not meeting those minimums, then we need to scale up this design base shear. So that's kind of the layout of what the code tells us to do. So like I said, the question is, well, we were just previously looking at base shear within the program, and we might be wondering, well, okay, well, which base shear out of all of these different variables is the program giving us? So I'd like to clarify that now. So base shear consideration according to RF-DYNAM Pro equivalent loads. Well, if you remember way back when, and I said this is a very important topic, we chose the type of spectrum in the add-on module to design spectrum for linear calculation. And this is actually going to give us the design base shear VD according to 418.12.7. But I do want to clarify that this does not include this additional factor here from 418.12.6. So like I said, there's criteria of when you should and should not include this factor. It is not included with this design spectrum. It does, however, include multiplying by IE, dividing by RD over RO. Remember, that was information that was asked for within this table over here on the right, so we certainly will take that into consideration. So the other option for the type of spectrum is the elastic response spectrum. So this was the second option under that drop-down. And this is going to give us that elastic base shear VE from 418.12.5, which means that absolutely no factors are considered. So it does not include IE and dividing by RD and RO. These are taken out of the equation. So we might use this for, first of all, calculating V sub E if we need it, of course, but also for lateral deflections according to 418.13.2. So we might then further be asking, well, okay, if I can't take this factor into consideration automatically within this table, or what if I need to scale up my design base shear? How can we do this within RFEM? And the answer is with that factor option that I previously showed you. So within the response spectrum directions, X, Y, and Z, we can apply an additional factor here if we need to account for the factor back from 418.12, or if we need to scale our base shear. Okay, so then going back to the presentation today, what I'd like to do is to go back into RF-DYNAM Pro. So if we go into our add-on modules, and once again, we launch RF-DYNAM Pro here. The last thing I want to do is just, like I said, discuss these drift or deflection considerations. So as we just saw within the PowerPoint, what I'd like to do here is to make a copy of my existing response spectrum. And we're going to rename this one elastic. The type of spectrum, as we just talked about in the PowerPoint, is going to be elastic response spectrum. So now notice that all of this information was copied from my previous case, but I'm no longer asked for the variables IE, RD, RO. This is taken out of this consideration, so no factors at all. Well, under the dynamic load case now, we'd want to also make a copy for our dynamic load case 2 here, and we'll rename this one elastic. Again, most everything stays the same except for this second tab here. Instead of assigning the response spectra for design, we now have two different options here from that previous tab. So I'm going to choose my elastic. Now, the factor, as I mentioned, is available here. For this particular case, we're probably not applying any factors. But of course, if we jump back to dynamic load case 1 here for design, this is maybe where we want to scale up that base shear, apply that as additional factors. So for drift considerations, we still want to consider accidental torsion. We'll still export our load cases and our result combinations, and we're ready to run our calculation. So once again, I will open up here our last model for the presentation with saved results. What you'll see within our drop-down box is twice the number of load cases and twice the number of result combinations. And that's just simply because we have our dynamic load case 1 for our design response spectrum, and we have dynamic load case 2 for our elastic response spectrum. When we take a look at our table and we visit our table 5 here for dynamic analysis, what you'll notice within our drop-down box is we have our natural vibration case from way back when, and now we have 2 dynamic load cases here as well. So let's take a look once again at our result envelope in the X direction for that elastic case, and we can turn on our results. So looking back at the members, and I'm going to take a look at the shear in the local Z direction. So we're taking a look at our result beam here. This base shear would be that V sub E directly from the standard with no factors considered. So that's definitely a significant difference here between the base shear that we saw before versus the base shear with the elastic response spectrum. But I'd like to take a look at deflections or inter-story drift. And when we refer to the standard for this, we're going to take a look at sentence 418.13.3, where the code tells us that the limit for the inter-story drift for maybe our structure today should be something like 0.02 or 0.025 times HS. And HS is going to be that inter-story height. Well, for our case today, the inter-story height between our levels here is 3.5 meters. So 3.5 meters times, let's say, 0.02 directly from the standard gives us a limiting inter-story drift of 70 millimeters. So how can we tell the drift here then for each one of these stories? Well, once again, turning this to that wireframe view, and let's take a look at the plan view. I'm going to highlight those exact same nodes that we use for our result beam. And going back to an isometric view, you can see those nodes highlighted right there in the center. Well, I can right click to turn off the hidden objects in the background here. And actually, let me show that once again. And we'll create a isometric view and choose the visibility by the selected objects. Okay, so when I right click, previously this is what was shown with those hidden objects kind of shown in the background here, but just to give you a better visibility, we can also turn those off by right clicking and turning off the visibility in the background. So these are just the nodes that exist right up the center of those different stories. So I'd like to turn on my results again, and I'm going to jump to the global deformations here under my project navigator in the global X direction. And now you can see the deflections here for each node. Now, just a tip, the nodal deflections are not turned on by default. So if you're trying to do this on your own and you're realizing, okay, I'm not seeing any deflections at all for my nodes, under the display tab, you'll see this results tree. And everything under the display tab here within the project navigator just really controls what we're viewing graphically here. And in particular, we'll see this whole colorful section here for results. Well, under deformations, you'll want to turn on the nodal displacements because that is turned off by default. So now we can view the displacement at each one of these stories. So looking at the very bottom, of course, we have 0 deflection where our supports are. We look at the first story, we have 0.9 millimeters. And looking at the third story, we have 2.7 millimeters. So the inter-story drift would be that 2.7 minus the 0.9. Taking a look at the story above it, the 5.1 minus the 2.7. And we continue to do so all the way up to the top here, where our top deflection will be 30.2, but the inter-story drift will be 30.2 minus 26.4. So again, we'd want to refer to the standard here for those minimum inter-story drift requirements. And for our case today, we're meeting those, so drift seems to be not a concern. What else you can do, one final thing, is you'll notice that I currently have all of these nodes graphically selected here. And I can go to my table, and it will take just a minute here to populate, but I can view my nodes, the deformations for each node. And let's see, selecting these nodes again, we have this nice feature here where I can show the selected objects only. So taking a look at this table, these are only the nodes that are relevant to what I have selected here. And as we'd expect, we can take a look at the displacements and see the gradual increase here of displacements in the X direction as we move higher up the structure. We can export this to Microsoft Excel just with the click of a button here in the toolbar. It'll export only the this table here, so that maybe we want to do some quick drift calculations or inner story drift calculations, we can do so within Excel. Okay, so that will conclude our webinar today. So I will jump back to the PowerPoint just to sum up a few points. I always encourage everyone to visit our website at dluwall.com if you're interested in learning more about RFEM or any of these dynamic add-on modules. As I also mentioned a couple times, we have these previously recorded webinars, technical articles, frequently asked questions. This is all shown to you on our website. We do have some online trainings coming up before the end of the year. So if you visit our events page or online training page, you'll be able to view those, see when they are, and register for them. And for anybody today that has yet to be in the program RFEM, feel free to download the free 90-day trial version on our website. So this is full capability. It includes all add-on modules, and it's for a duration of 90 days. So if you have any questions or comments about today's presentation or anything else, feel free to contact us in our Philadelphia office, and you can see the phone number down at the bottom at 267-702-2815, and our email address is info-us@dluwall.com. So we will have many more upcoming webinars. You can register on our website at dluwall.com under support and learning webinars. As many of you know today, I tend to send out a reminder email about a week before these will take place, so feel free to register directly through the email as well. Many of you are wanting PDH certificates for today, and these will actually automatically be emailed to all participants that were available for the full presentation. So this is a requirement for the various states that were pre-approved providers that attendees are here for the full 60 minutes in order to issue that PDH certificate. Again, they'll be automatically emailed to you, usually within the next day. It doesn't happen right after the webinar, so just be a little bit patient with that. If there were any additional attendees and you watched today maybe under a colleague's registration information and you yourself did not register, then you will need to request your PDH here at info-us@dluwall.com. So again, if you did not register with your own name and your own email and you were here for the full 60-minute presentation, feel free to send us a request for that PDH, again at info-us@dluwall.com. And with that said, I want to thank everyone for attending today. And as always, we hope to see you at our next webinar. Thank you.